Okay, so I just finished implementing this struct thing in the noname project that I've been talking about in the previous video, and this allows you basically to kind of like Rust. I mean, exactly like Rust, basically, to create your own structures with like fields, and it's still bare bone. Like you cannot actually pass a struct as an argument of the main function or return a struct yet. But you can define them in your code and use them like this. And you can actually have nested structs, but not everything will work. So if you have like something like that's not gonna work. I still need to implement that. So it's quite limited. And well, it doesn't matter. It's it's making progress. Things are evolving, so that's good. But there's still a lot of work. What I want to do in this video is kind of see if there is a bug in my implementation, and basically look at the output of something like this, just to see if there is if the constraints make sense. And so basically that's always what I'm doing. I always look at the output of things when I implement something, just to make sure that everything makes sense. And that's what's nice with noname, is that we get a nice output. So anyway, we get this output, but I'm just gonna go run it in debug mode. So it works. This example works, and I can, to prove to you that it seems to work, I can try and pass a different y here. So if I pass 3, it will fail to verify this. So let's try that. Go to debug, and it seems to work, right? Invalid witness, row 5. That's not a very helpful error message here, actually. But it knows that there's something wrong. It knows that there's one of the input paths, like this assertion is not passing. So that's good. And I can also try to write a constant in the code that's not equal to y here, and it tells me again that this assertion failed. This time before we even try to create a proof. Maybe we should have different errors. This is a compile time error versus a proof creation error, but whatever. So anyway, this seems to work, right? I'll run it one more time. Proof created, proof verified. Okay, let's run it in debug mode. And in debug mode, we can see the witness, we can see everything. So let me just copy that on the right. I think that's gonna be easier to read if it's on the right. Close this, close that, and now we have our gates. And maybe I could even, should I create another? I never do this, but maybe this will be helpful, and maybe we can analyze the program like this. So okay, these are our gates. So we have a public. Wow, it's actually messed up here. Maybe I can do it something very quickly. I can make it prettier. This is a hack, but it already looks better. Okay, so the first gate is a generic gate, and it is saying it's a normal public input gate, and it makes sense. We have a public input, it's a field. I've already explained that in the previous videos. I'm not gonna, that's correct. I have a second public input, the y argument. So I have 2 public inputs here. So another generic gate, sure, that makes sense. Encoding the constants. Okay, these are constants, right? 1 and 2 are constants, so we need to encode them in the circuit because we're gonna assert something on them later. So this seems to make sense. Here we're encoding the constant -1, and here we'll encode the constant -2. There is a thing in between. So interestingly, that constant is used right away to assert this thing. So maybe you would have thought that x1 and y2 are created here, so we first create 2 gates to constrain these values to encode the constants. But actually this thing doesn't really exist yet. It's just something very abstract, and only when these constants are used in actual constraints, they are encoded in the circuit. So constants, it's very possible that we actually, we create a constant like z equals 3, and then we never use it, and so it doesn't make sense to constrain that constant. So The code will never constrain that. So it's only constrained when it's used in something like that. Which might be a bit dangerous in the sense that if you write these gadgets, you really have to make sure that you constrain these constants. Otherwise, you're not really doing anything. But it's also inefficient because then it means that every time you use a constant in your programs, then it's going to use a bunch of constraints, and that's not very efficient. So that's kind of a trade-off of security versus performance. And I could actually add a mode that would add a constraints every time I do something like that, no matter what, and maybe that would be interesting if you're really, really paranoid. But I don't have that. So yeah, that's a design choice. Okay, so anyway, we added the constant 1, and you can see the constant coefficient of the generic gate is used to constrain that the left value here to be 1. Same here for the left value here is constrained to be -2. And then we do the asserts in line 12 between that constant and the public input. So let's see if there's a wire, right? And we actually constrain things like that. The constant is on the left here, and the variable is on the right. So the variable is x, the constant is thing.x. And this is how we constrain that they're equal. We just check that the subtraction is equal to 0. Very, very easy. Okay, how do we do this? I guess we should make sure that these things are wired properly, and so this is what's happening here. The x of the public inputs of the argument here needs to be wired here. So indeed, that was in gate 0 that we encoded that public input, that x. So gate 0, the left value, or the first value of gate 0, and it gets into the assert equal here, which is gate number 3, right? So gate number 3 here. Maybe I should write that properly, by the way. Maybe I should write gate number 3, but I think it's clear enough. If you have any feedback, you can tell me. And it goes in the second position. So that's interesting, right? It is a variable, right? And the variable is in the second position. That's what we see here. So yeah, I think that's correct. And then the second wiring is the actually I don't care about that. I really care about the wiring of this x here, right? We encoded this constants in gate 2, so we need to make sure that gate 2 also acts in this gate 3 here. I'm going fast, but don't hesitate to pause the video, I guess. So gate 2, gate 3, we'll get it here, right? X equal 1, we encoded that in gate 2, that's the first value of gate 2, first value here. And we make sure that it's equal to the first, the constant here, so the first value in gate number 3, And I guess the same thing happens here. Maybe I don't need to do that. If it's correct for the first value is probably going to be correct for the second value, but we can check it. This thing is wired here, so this is gate number 5 here, the second assert equal. So the first gate, I guess, if we start counting with 0, is wired to the 5th gate, second value. This is correct. And then we'll look at thing y, the constant that we encoded in gate number 2. Well, okay, that's weird. 4050. Okay, we might have a bug here. Gate 5 is indeed the assertion. Oh, gate 4 is when we encode the constant y. Oh yeah, gate 2 is when we encode the constant x. Okay, so never mind. Gate 4 is where we encode the constant y. So we do go from 4 to 5, and 5 has the constant, that's the first value, right? So 5.0, and 5.1 is for the variable, the public value. Okay, everything seems to be correct. I convinced myself. You can try and convince yourself as well. And we can look at the weakness, and the first value in the first column is, I'm passing 1, if you remember correctly, and the second value I'm passing 2. So 1 and 2, this is correct, so my witness, my public input. Then for gate number 2, we constrain the value 1, so I have to put a value 1 here. If I don't put a value 1, it won't work. Gate number 3 is the asserts, left and right. Left and right are the same value, and the assertion for gate 5 is going to be the same, right? They have to be the same value. It's 1 and 1 and 2 and 2. 1 and 1, oops, 1 and 1 here, and 2 and 2. And this is the encoding, gate 4 is the encoding of the value 2. So if I put something else than 2, it's not going to be 2 minus 2. It's going to, if I put 3 here, it's going to be 3 minus 2, and it's not going to be equal to 0. So it seems like my circuit is correct. Verified the gates using my debug messages. I verified the wires, the wiring, everything's good. We're not returning anything here, so that's all we need to do, and the witness is correct. It's a very simple example, but we can already see that if that simple example is correct, probably bigger examples are going to be correct. But if we do something funky, we might want to verify that the constraints make sense compared to what we wrote here. Yeah, I guess that's it. As usual, I'm going to continue doing these videos, I guess, as I continue developing this noname project, where you can write Rust-like programs and prove them. And yeah, if you have any suggestions, or if you want to play with it and something doesn't make sense or something doesn't work, let me know. It'd be nice to have other people playing with it. I don't think anybody's playing with it but me at the moment. So yeah.